Without further ado, let me introduce our speaker. Our speaker is IR Saifuddin bin Shafi'i. He has over 17 years of civil engineering experience in the design, construction, and safety of large infrastructure for hydropower and mining sector. He has participated in various projects in Australia, Canada, Malaysia, Papua New Guinea, and Indonesia. His major assignments include dam and tailing storage facilities, tunnel and underground structure, mining waste dump, rock and soil slope assessment, dams safety review and management, oil and gas pipeline, coastal protection and risk assessment. So without further ado, let us welcome Ayah Saifuddin.
Thank you, Engineer Fu. Assalamualaikum and good morning, ladies and gentlemen. Now, today, do you know that Malaysia is actually one of the 192 countries in the world that has agreed to embark on this sustainable journey to be part of the 2030 sustainable agenda. This agenda is actually an initiative by the United Nations, whereby the objective here is to have a nuclear-free carbon country by 2030. As an engineer, what we can actually contribute, in fact, during the meeting in 2015, we were represented by the Prime Minister. They have identified 17 sustainable development goals, as you can see on the screen. And as an engineer, what we can contribute is really sustainable on the SDG number 9, which focus on the infrastructure. Now, the takeaway points, I will leave 3 takeaway points from my presentation today. One is sustainable solution is not just about environmental friendliness, green solution. It is more than that. And throughout the presentation, you can see from several examples, the sustainable solution in certain conditions proved to be a more cost-effective solution as opposed to the conventional solution, without compromising the technical requirements for the project. For instance, the durability, the safety factor. So this all can be met because it comes to the point number 2, which is right engineered solution. All of these solution of materials is an engineered material, so it obeys physical laws. So what does this mean is you need to understand not just the material properties, you also need to have a grasp on the engineering principles, talking about soil mechanics, the rock mechanics. So if you're dealing with river works, you need to understand how the mechanism of hydraulic works and the loading, the hydrology aspect of the things. So this one, you really need to have a good understanding on both the material property and the engineering principles. And lastly, what we going to cover today is the performance specification. Now, performance specification is different from the traditional specification. So what you have here is a specification that specify really the engineering properties of the product relates to the design assumption. So for instance, in your case, as simple as separation function. So for separation function, you would normally require the pore of the separator to be large enough for water to pass through it and small enough to retain the particles. Now, in terms of the geosynthetic for the non-woven, instead of specifying the whole product properties, what you can actually do here is you need to only specify the critical properties that relate to your design. So I just mentioned just now for geosynthetic is the apparent opening size, AOS 95. And in certain case, you may be looking into the CBR puncture resistant if you want to place this separator against maybe a gravel aggregate, which is have a large sharp and large edges particle that may punch through your geosynthetics. Now, okay, in terms of the application, what we're going to cover today, we have divided it to several category. And if you look at here, this is a simple problem that you have on the floodplains. Normally, you're talking about floodplains, you will have a weaker ground. The conventional solution that you're normally looking at is the pile, either pile to sand or pile to length, all right? And in terms of the sustainable solution, what you can actually do here, you introduce the element of vessel reinforcement, and you maybe want to combine it with PVDs. That's one. And then also talking about space restriction nowadays, base side is almost gone. You will live with a very narrow ROW. So you have to build a steeper embankment. So what you can use, what you can actually do here, you introduce the reinforcement element into the field so that you can able to build a steeper embankment, talking about 60 to 70 degree slope angle. And pavement, yeah, this is also something new. You can actually improve the design life of the pavements. Um, later we'll talk about this one also. And another scenario, infrastructure projects, road works, you will have to cut through the hillside. So talking about the balance of cut and fill. So on the left, you have to maybe consider the hydraulic works, the channel bank improvements. So maybe you have a river crossing, to keep looking at the box culvert. What are the anti-scouring measures that you want to look at? And then you will also have this rock slope, maybe rock slope on the cut sections, and what are the things that you can actually do instead of strengthening the slope. Maybe because of the limited budget, what you can do here is to install a rockfall protection, which is more cost effective as opposed to strengthening the whole slopes. And this one, similar to hydraulics and rockfall protections, element of risk management is involved. And then you start to be looking at what are the risks to the public, whether it's a low risk, high risk. So those kind of things, these are the consideration that you have to consider for the selection of the sustainable solution. And lastly, this one you can actually see here is basically cutting through mountains. And this one is one of the another transportation project, railway. So what you can actually do to minimize the risk of rock falling and affecting the asset that you want to protect here. Now, the content of presentation today, I've divided it to five topics, subtopics. Topic number one is the fact and fallacy. In this one, I will talk about the misconception of sustainable solution and what does this mean actually. So we will try to set up the true fact of this sustainable solution, and then we'll cover in details on the walls and slope, rockfall protections, and I also give you an introduction about the roadwork improvements, like for instance vessel reinforcements, the pavement reinforcement, and lastly the erosion control and drainage is more related to the hydraulic works. We'll go on the concepts and what are the engineering principles, and then you're looking at what are the some mitigation measures that you can actually implement in terms of the sustainable solution. Now, this is our first misconception. Point number one is actually sustainable solution is about green with low carbon emission only. So this fact is not quite right. Okay, what does this mean? It's not just about lowering the carbon emission. We want to also recover back the carbon that has been released. So the sustainable solution allow for environmental integration, and you can see here this is actually a reinforced soil slope that we are using the double twisted mesh facing, and you can't even see the steel mesh anymore after a few years. Or in fact, our experience in Malaysia, you will start to have this even after several months, because we are a tropical country and grass can grow faster than that. Now, the whole idea is once this vegetation is been established, you will recover back. So you're talking about the carbon sequestration. And then this one is one of the project in Italy. Is actually in River Reno. And you can see here the gabion installed in 1994, and it's more than 100 years now. And you can see that the structure is still there. It's durable enough to meet the design life. It's more than the design life that has been designed for 100 years. And you can actually see that the vegetation, the environments, the plant integrate well with the structures, and you can't even see the structures anymore like the one that you used to have when during the end of the construction. Now, this one is another one. You can see here along the riverbanks. So tree can grow through the gabions and it blends well with the environment. Now, there's now also when we talk about sustainable solution, it's not just about the environmental friendliness. If you design this correctly, you can even use this solution for many type of situation. You're talking about building a field over weaker ground, or you have to maybe utilize the amount of excess cut that you have from the cutting section, and rather than using a granular backfill, you can actually use this material, low holding distance, which means low carbon emissions, and you introduce the element of reinforcement into the materials and allow you to build a steeper slope with it. And yeah, this one again back to point number a point earlier, scarcity of materials. So what I can say, when one of the highway project that we working on is still ongoing project, they have got about 3 million excess cut, and what they do here, they utilize at least 60% of the cut as the field materials for the field section construction. So this one you're talking about introduction of high strength reinforcements, introduce the facing vegetated facing on the front face of the reinforced soil. Now, sustainable solution, because this one is also an engineered product, it's all been assembled in the factory, and you're talking about the productivity. One of the advantage, some of the product is modular. So what does this mean is it all been assembled at the factory. You just have to proceed with the field placement, for instance, for the reinforced soils construction, and you can see here from the picture, right? So all of the material is being assembled at the factory. It is quick to install, and it doesn't require a skilled workers to do it. Now, fact number 2 that we want to cover today is sustainable solution is not comparable to conventional solution, right? This is not, this is pretty subjective, I think, because we as engineer, we always relies on precedence. We wanted to design something with a material that we are comfortable with based on our past experience. That's why through this talk, it's a good opportunity and platform to introduce a new solution. And at the same time, this is not a magical product. It doesn't work wonders if you don't obey the engineering principle behind it. And this one is 80-meter high rock facing wall. All right. This one, and just talk about the durability. If you look at this gabion, some of the argument that we have in Malaysia is gabion is meant for temporary works. Later, I'll show you that the gabion, if you design the right coating, it can be designed up to 120-year design life. And this is all been covered in the British Standard 10223 together with ASTM A975. Now, when you also talk about the durability of one of the sustainable solution gabions, one of the issues that you normally encounter is the corrosion on the gabion. What happened here is because the coating is actually the defense, the lines of defense for the gabions. So once the coating is exposed, those base metal exposed to atmospheric condition, and we start to have corrosions. And when you have corrosion, you will have this issue with tearings of the gabions, and eventually this rock fill in the cage will just wash out into the river. Now, what does abrasion mean is, here you can see from the video, in our river, normally you have these high suspended sediments, and these suspended sediments actually apply these abrasion forces to the coatings. And over the time, throughout the exposure, during the design, during the service life, you can start to have the reduction of the coating layer. So one of the advancements that over the years, they are what we call the advanced coating, where it have a higher elements of abrasion resistance. And later I'll show you how you can actually verify this abrasion performance through the laboratory testing. Now, this one is a new standard, a new clause that have been added in ASTM 8975 2021, and you can see from this clause, abrasion resistant test has been added into the test index. So this abrasion test, what it does is it compare the performance of advanced coating, polymer coating, as opposed to the typical polymer coating that normally used in Malaysia, which is PVC. All right, and you can see here, this coating will have a better resistance to abrasion. What the tests do here is they try to scratch the coating and measure how many cycles it takes before the base layer of the base wire is start to expose. And just for comparison's sake, you can actually see that advanced coating, you will get about 450 cycles, as opposed to PVC is only about 50 cycles. So these are some of the additional product innovations that been introduced in the market. Then, and if you think that it is suitable for a project, especially on the river works, you can actually explore as a solution. Now, this one is just to show the how the test been carried out, and you can see here these are the machine, the equipment, and so what does this do here? It tries to scratch the coating layer that protect the base wire. So you can see here the lab technician try to assemble it. All right. It's a very simple and fast test, and you can done it in less than 10 minutes. So I was maybe bring it forward. I just want to show you how they actually measure the cycles. So this is when the test started, right after the assembly. So you can actually see we try to measure the amount of cycles for the coating to start to expose. So you can see after few minutes, you can start to see the breakthrough and the base wire is being exposed, and you record down how many cycles it takes. Okay, now in terms of durability, gabions is not a simple structure. Actually, there's many engineering principles behind it. One of the engineering engineering properties that you need to understand is really the coating. And you can see here, Malaysia normally we're looking at C3 environments. For gabions in subtropical or tropical zone, it fall under C3. And within coating, you can actually have about 10-year design life, right? And with this Galfan coating, you introduce about 5% of alloy or maybe 10%. The design life is about 25, 50 years. What I want to share with you guys today is for the high aggressive environment, C4, which is the lowest category under the wet environment. Okay, we are talking about the river works. With zinc coating, it's not even being covered in the design life. So basically, with zinc coating, you're not able to even meet the 1-year design life. And then point number 2 is actually, as you can see here, there's some specification where it requires zinc coating plus PVC. All right. Even if you do that, you can't have this 120-year design life, because the codes actually says that you need to have, if you want to have a 120-year design life, you need to be specifying the Galfan coating plus the polymer coating. All right. So this is just to give you a brief introduction about the coating requirements, hence the durability aspect of the sustainable solution. This one is without the polymer coating. You just rely on the metallic coating itself. All right, even with different classes and different content of aluminium, you can see the magnitude of the design life changes is at least twice more than what it used to be for zinc coating. And then if you add in another 5% for Gulfan, you will get 50 years instead of 25 years design life. So all of this is based on your design requirements. Selection of the coating is one of the important aspects. Now, moving on, we focus on the walls and slope. Now, statistic. I found this is very interesting statistic. You can see here, Malaysia is actually ranked number 10 for the highest frequency in the world in terms of the landslide occurrence, according to NASA. And this is an alarming things, actually alarming fact, because it means that we really have to design, let's say you want to build a wall and slopes again the hillside over the floodplain. You need to design it based on the good engineering principles, right? Okay, and then of course, once you start to have these landslide failures, you can see here the study by University Putra Malaysia. You can see the estimated economic loss is about 5 billion US dollar, is about 5 billion ringgit. Now, when we talk about slopes and wall for sustainable solution, okay, there are two example here. One is if you use gabion. So gabion is actually a mass gravity structures. The one on the right is what we call reinforced soil structures. Now, if you still use gabion at the facing, but the difference here is the gabion act only as a facing. It is there for erosion protection purpose, and the stability of the slope is actually being controlled by the element of horizontal reinforcement that been placed at certain vertical spacing over the height of the slopes of the walls. So now, basic concept of reinforced soil structures. So as you want to build a steeper slope with reinforced soil structures, okay, you will have a tendency for the slope to fail at a certain angle. So we're talking about normally 1 to 2 for the field slope, and maybe cut slope is about 1 vertical to maybe 1 horizontal. Now, this is what happens when you try to build slope of more than maybe 45 degree of field. Now, what we can actually do here is we introduce the element of reinforcement. It can be in the form of geosynthetic or metallic meshes. All right. It doesn't matter what type of material you want to use, but the whole idea is to increase the tensile resistance of the field, and eventually we increase the apparent shear strength of the whole field materials. And the things that if you look at the right, now, the reinforcement need to be long enough, all right, to be embedded into the passive zone, which is the stable zone. Now, the active zone is actually the critical failure plane that you already identify when you do the stability analysis. The length of reinforcement will, you need to make sure that it is of a sufficient bond length to prevent the pull-out failure modes, whereas the strength of the reinforcement need to be sized correctly to prevent the rupture failure mode. Now, similar concept for any shear strength shear strength concept, we talking about shear strength is actually a function of effective stress. So the higher effective stress it is, the higher shear strength. Now, when you introduce the element of reinforcement, it basically in a way adding a additional force resistance in terms of the tensile strength, and eventually increase the overall safety, overall stability of the slopes of the walls. Now, this one is just to illustrate another concept, which is also contributed by the geosynthetic reinforcement, and you can see here, in this case, is the geogrid, right? With by having this geogrid, you can actually have the confinement effect. So basically, it increased the confinements, which is the sigma 3, the lateral resistance of the field materials. And you can see here, the one on the left is unreinforced, and the one on the right, you can see with introducing a series of the geogrid into the field, right? The field can actually take the load of about 15 kPa. The size, the weight of this guy is about 75 kilos. Right, this is just a simple example experiment that you can actually carry out also at your home. Now, when we talk about reinforced soil structures for slopes and wall, the difference is actually the cutoff is at 70 degree. Right, this one is taken from BS 8006. All right, and you can see here, the one on the left is what we call reinforced soil slopes. Is gentle than 70-degree, whereas the one on the right is reinforced walls. Now, there are several components, also important component beside this reinforced backfill. One is actually the reinforcement, okay, and then the drainage blanket. You can see here drainage blanket being introduced. Now, if you're talking about utilizing the non-granular backfill, these are the things that you need to consider, because if let's say you have external groundwater, especially if you place these walls or slopes against the hillside, where there might be a higher groundwater table at the natural slope, all right? So you need to be sure that you add in this drainage blanket and design it correctly based on the capacity you want it for. So this is also one of the common problems. And if the blanket is being under design, all right, it will cause a build-up of pore pressure. And once you have this build-up of pore pressure, because water got no way to go, it will tend to push the structures and create maybe a sliding failure mode. Okay, for the reinforced soil structures, there are actually two um, components that you have to design it for. One is the tensile strength. Normally, when you talk about when you talk about okay. So when you talk about tensile strength, you have short-term tensile strength and long-term tensile strength. So short-term is not the one that you use for the analysis. You should be using what we call a long-term design strength. So this long-term design strength is actually the element of reduction factors that you introduce into the ultimate strength. So basically, if you specify a geogrid with ultimate strength of 200 kilonewton, you can't be using this 200 kilonewton per meter in your analysis. You need to check with the manufacturer what are the reduction factor that you should introduce. Okay, there are several categories. One is the creeping effect. And normally this is the highest reduction factors. And you also have the installation damage, which is the function of the type of fill material that you use for the backfill. Okay, so if you have gravel fill, of course, it will have a higher installation damage as opposed to maybe sandy or silty particles. And then lastly, the durability. So durability over the service life, it will be exposed to chemical and biological degradation. So you also want to introduce this reduction factor. Now, in terms of the materials, normally for the reinforcement, that is why people often look into the PET, all right, polyester, and also for the steel, you maybe also can use a steel reinforcement or steel meshes, because steel will have the lowest reduction factor as opposed to geosynthetic, because it has a higher durability resistance as well as the installation damage. All right. Now, this is just to illustrate what I mentioned just now, long-term design strength. You can see here 40 kilonewtons. After the reduction factors, you will only get 18 kilonewton. So this is very important. You do not want to be using that 40 kilonewton for the analysis, and you will end up with a overestimate of the safety factor when you check the stability of the slopes or the walls. Now, the second failure mode, just now tensile strength is all about rupture failure mode, whereby if you under design it, the reinforcement will rupture, and then the field basically lost the support and you start to have failure. And then the second failure mode is actually, you're talking about the interaction with soils, pull out and sliding. Just now I've shown you the active and passive zone. This is where it came in. So you need to be sure that you have the right amount of anchorage length within the passive zone to prevent the reinforcement being pulled out away from the field, right? So it's all about the soil reinforcement interactions. I mentioned in the early of my presentation today, this is all engineered products, so you need to still compact the field. you still have to compare it to 95% MDD, 98%, 90%, depending on the project requirements. And by having this compaction, you will have a closer bond, intimate contact between the soil and reinforcement. Okay, because reinforcement won't work without the contact of the soil. So it relies on the contact with the soil to be able to provide the tensile strength to the field. Now, this is just to illustrate the two common failure modes for the interaction we saw. One is, I mentioned it a few times already, bond or pull-out failure, where if you don't embed it long enough in the passive zone, then you would have the pull-out failure modes. And the number two is actually the sliding, and this is where you check it based on these typical values of pull-out coefficient and direct sliding coefficient. So it varies according to the type of material. So the gravel, of course, will offer a higher pull-out coefficient as opposed to maybe sand or even silty and finer material like clay. Now, in Malaysia, how you actually do the reinforced soil structure design, reinforced soil walls design, you can actually use these two methods. One is what we call allowable state design, where you don't introduce any element of reduction factors in the materials and in the uncertainties or maybe the subsoil condition. You're looking at maybe safety factor of 1.3 or 1.5. And another perspective is this one is it's actually been introduced many years back, but the usage is still less in Malaysia. LFRD limit. So this one is really you start to introduce the element of reduction factor similar to long-term design strength, and the end product here you're looking at the safety factor of more than 1 instead of 1.3 because you already introduced the reduction factor on the materials, on the uncertainties of the analysis. Now, okay, in terms of reinforced soil structures, just now I mentioned facing option. So I'm going to focus more on these three facing options. One is the gabion facing. The second one is the vegetated facing. And the one on the right is actually upgrade version of this gabion facing where we introduce the elements of welded panel, smaller welded panel really, and it allows for a smaller rock fragments being installed. Now, this is how it looks like stone facing option. You have the gabion facing, and those mesh reinforcement, those extended tail is also can act as like a reinforcement. And normally for this type of application, if you're talking about maybe 6 meter high of wall, you may not have to use the geosynthetic reinforcement. You can actually rely on this metallic mesh reinforcement for the design. Now, you still need, you can see here, rock facing and fill material. So those two material is not compatible. So you need a separator. For this case, we're using non-woven geotextile. So it helps to separate between two non-compatible material, which in this case is a rock and a finer fraction of fill. Now, this is one of the project is Klang Valley Expressway, ongoing project. They use this reinforced soil structure system. Why they use it is because they have this excess of cut. It's about 3 million cubic meters. And by having this excess cut utilized on the fill material, it helps a lot to save the overall project cost because you're talking about saving in terms of the hauling distance, try to import the granular backfill into the field section. And this one is another view of that project. It's about 35 to 40 meter high maximum wall height here. And this one is another one just recently be completed at KL Karak Highway, kilometer 66. So just to highlight the arguments that sustainable solution is not meant for the durability requirements. So you can see here, if you design it correctly with the right coating, it can take design life up to 120 years without any problem. This one is at Istana Sharkia. They use this system for the access road to the palace on top. All right, and you can see here the environmental integrations. You try to recover back some of the carbon being released, hence why you allow this is allowed by the having this vegetation grows on the face of the gabions. And this option also can be integrate well with any reinforced concrete structures. Now, this one is at the river banks. All right, on the river banks, this rock fill facing option is also can prove to be a viable solutions. We'll cover this more later, but basically, by having a rock facing, it has a higher roughness. When you have a higher roughness, the velocity along the river start to slow down at the contact of this. Between at the contact of this gabion and the fluid. All right. And this one is just to illustrate another benefit of this reinforced soil structure system. All right, you can see here, because it is not a rigid structure. One of the advantage actually for any reinforced soil structure is they are flexible. But then again, the flexibility is in terms of the reinforcement as well as the facing. Okay. You can see here, this structure is actually being used in the frequent dynamic loading condition where it has frequent vibrations being transferred over to the walls or reinforced soil structures. And this one again, for TMB projects, it is a suitable option not just for new projects, rehabilitation works, especially talking about riverbank improvement works. You can actually use this system provided you design it correctly. Now, this one is I just want to talk about the stone facing option number 2. All right. These are the weather panels that we introduced at the front facing, and by having these, you will have a more cleaner look on or in terms of the aesthetic appearance of the overall facing of the reinforced soil structures. And this is how it looks like in Romania. 22-meter high motorways using this reinforced soil wall solution. And you can also be, instead of gabion, you can actually use this system also, okay, on the culvert inlet and the culvert outlet. This one is what you have in France, motorways in Montenegro. Now, another concept, another design of this reinforced soil structure, because normally reinforced soil structures, the length has to be about 70 to 90% of the slope height. What with this shoring MSE wall option, you will be able to reduce the length requirement to 30% height or minimum 3 meters. So what does this do? It transfer the reinforcement, the loads to the soil nails or the anchor of the cut slope behind this field. And this one is actually applicable for maybe a road widening project where you're talking about maybe extending few lanes within your ROW, and you don't really have space. If you want to build maybe 10-meter high, additional 10-meter high field, you may need 7-meter space, but by having this, you only need about 3-meter length of space to be able to have a similar performance structure as the typical reinforced soil structures. This is one of the recently completed project that we have in Taman Rusa for Dixons. You can see here it's about 6-meter high reinforced soil structures at the toe. And from the picture on the right, you don't really see any geosynthetic reinforcement because we don't really use any of it. We just rely on the mesh reinforcement as the reinforcement to reinforce the backfill zone. And this one 6-meter high, we only use 2-meter length of reinforcement, and another 1 meter is for the overlapping length. Now, just now we talk about road facing option. What if you want to have a vegetated facing options? This is just to illustrate the modularity on one of the system. It come pre-assembled at the factory. You don't need skilled workers to do it. You just have to open up the facing the cage, and you start with the filling process and compaction process. This is how it looks like in real life, Elmina West, where they use this vegetated facing system for the reinforced soil structures along the river banks. And this one is at KKM. You can see here they combine vegetated facing together with the rock facing. And the one on the right, just to illustrate the ease of installation of this modular system. And in terms of production productivity, we expedite the construction time, hence saving costs for the projects. And yeah, picture on the right, you can see after several months, vegetation start to grow, and yeah, you start to have this vegetated facing. This is another project that we also work on, Sabah Sarawak Gas Pipeline Rehabilitation Work, where they have to use the local laborers there. You're talking about utilization of majority of the unskilled workers for the slope repair, and this sustainable solution proved to be a cost-effective solution, especially in this case, not just the skilled worker requirement, it is also meet the, because it is access, is the remote access project, and talking about the access to the site is very difficult, and by using this sustainable solution, you easy to transport and yeah, easy to install basically. This is how it looks like, overgrown vegetation after several months. Now, I would also want to introduce another element of infrastructure structures. Just now we covered shore MSC wall system. This is a hybrid structure system whereby it introduced the concept of primary and secondary reinforcements. And by having this reinforcement, you can actually see that you can increase the vertical spacing of the, for this case, a geogrid reinforcement may be more than a meter. You can even use 2 meter or 3 meter with this concept. So basically, the secondary reinforcement will control the shallow failure modes within the 3 to 6 meter from the edge of the facing, whereas the primary strength is being provided by the high strength geogrid installed at maybe 2 meter vertical spacing over the slope height. And this is one of the project that use this one. This is a dry dock project. It involved frequent rapid drawdowns, right? You can see here is a place where they used to repair the ship, okay? And the water is being drawn down frequently and increasing it frequently. And the reinforced soil structures serve the purpose very well, even under this condition. This is another project, and you can see here the upper portion. You can see how many meters is about maybe 2 meter, 3 meters of vertical spacing. So it is possible to increase the vertical spacing of the reinforcement if you design it correctly. And of course, you need to also build it correctly during the construction stage. This is one of the project, again, 80-meter high, just now I mentioned in Sikkim Airport. All right. Just to illustrate the cross section here, 80-meter high, and you can see the element of drainage blanket. So for these high reinforced soil structures, you really need to be sure that you have tackled the any groundwater issues. Even though you use granular backfill, you may have to still consider this drainage blanket behind, because if you're placing it again hillside with a bigger catchment on top, more groundwater that may pass through behind your walls or slopes, then you need to really design the drainage blanket, or in dams they call it chimney drain, correctly to discharge the water away from the field section. So this is how it looks like, the completed project, and you can see the integration of the environments, and you hardly see any structures anymore after several years. So that is the whole idea of sustainable solution. Now, this is another new element. We call it mono anchor system. Talking about productivity in terms of the rapid intervention. This is a quite common one in Malaysia, where you have landslide at the toe and difficult to access the toe. And what you can actually do here, you can use this type of system because it is productive enough due to the larger area facing. This is about 10 square meters, so you can actually assemble this one in an hour time. Just to illustrate one of the completed project here, they try to have access from one side to another. And what they use, the beauty of this system, you can even combine it with the anchor reinforcement and install the mono anchor structures, and you place the field, and yeah, boom, you can have access from one side to another in just a few days or few weeks. depending on the length of the works. Now, reinforced soil structures, they are all subjected to failure. This one here, that's why I will keep mentioning about the drainage blanket. Water is the main culprit here. You can see here project the infiltration of water into the field. They use this clay structure field, and they have a bit of poor pressure, not just due to the infiltrations. All right, they also have the external groundwater influence. Even though they put in the drainage blanket, it may not be high enough to intercept all of the groundwater, and some of the groundwater pass through and build up poor pressure within the upper part of the structural field. And this is what remains. You can't even see the structures anymore. So it's always important to handle or cater for the water. And this is another sustainable solution that you can actually use. We call this drainage blanket solution. It's a geocomposite drainage. So instead of placing a sand drainage or gravel blanket at the back of the slope, you can actually use this one. It's made of polypropylene, and you can see those wave profile is actually to provide some sort of stiffness to the cores. And this one, for any drainage blanket, is all about the filter design concept. Two things that you need to check is really the piping and the permeability criteria check. You want the pore, right, between the particles to be small enough to prevent any piping failure modes, and it also need to be large enough for water to pass through it. So it serves dual function, separation and drainage, hence the term called filters. And there's also an argument that whereby if let's say you use the non-woven geotextile, there will be a sludge be up, and then this uh, drainage may get clogged, right? But really in actual case, you can see that this sludge be up is of low saturated density, and in any of the filter design, you just need the permeability of the water of the this sludge bill to be large enough as opposed to the natural material around it. Now, in terms of the subsoil or subsurface drainage, what are the things or engineering principle you have to look at? The most common one that everyone need to understand is Darcy law, right? It's all about the hydraulic gradients. Whether you use it for vertical application, just now for reinforced soil structure, you're placing it on the vertical section, or you use it below the road, that is more on the horizontal application, lower hydraulic gradient, so the water will pass through more relatively slower as opposed to the vertical application. And then, of course, again, you're talking about the coefficient transmittivity, which is what are the mediums that you use, whether you use sand, whether you use gravel. Of course, they will have a different coefficient transmittivity. And then again, they're talking about the flow net concept. And yeah, this is something that you also need to learn. And Study Green is actually a very good reference where it illustrate the construction of flow net for the slopes and walls. And filter concept, we already covered it in the earlier slide. Now, this is another problem when you talk about reinforced soil structures built along the river banks. You will start to have scouring. Okay. Now, how you can actually prevent is one of the options you can actually use is you embed the gabion maybe 1 or 2 meter below the riverbed. By having this, it will protect the toe. Just in case you have the loss of fines at the front, they will still hold the structure. Alternatively, if you want to explore another option, you can actually lay this mattress, and the length need to be long enough, at least twice of the depth of scouring that you expect throughout the design life. So by having this, more often than not, the most common problem along the riverbank, especially if we talk about walls and slope, is just about scouring at the toe. It's not really on the slope instability or the wall instability itself. And yeah, lastly, for the cause of failure for reinforced soil structures, you can see here similar materials being used on the left and right, but without the right construction, right supervision, you may end up with the condition on the left. So be sure that you supervise the works and follow the installation guidelines. And because this is a new product, this is something that you have to consider. And yeah, okay, that we already covered about walls and slope. We going to run through the rockfall protection and shock creep facing. Okay, now rockfall protections. Rockfall protection is often normally got confused with the reinforcement options. Now, what is the difference between protection and reinforcement? Protection is actually, in this case for rockfall, it does not stop the rock from falling, but it controls the trajectory of the rockfall. So basically, if you drag the slope, rockfall slope, rock slope with a netting, so instead of bouncing to the towards the highway, you can actually control the trajectory and collect it maybe on the ditch or the landing platform. Now, another things that you need to consider is rockfall protections has to work after you treat the global instability. Okay, the one on the left, there is not much concern on the global instability. So for this case, you can actually use rockfall protection because they're only having these falling rocks and they just want to contain this rock, and over the service line, they will mark it up and clear it. Whereas on the right, you can see here is a global failure. uh, Before you want to install any rockfall protection, you may have to explore the strengthening of the slope. You remove the debris, the loose debris, and look at the current slope now, whether you need to reinforce it with dowels. And the one on the right, basically, that is purely a global failure mode that is more critical. So rockfall protections are not going to be able to hold such a massive block of boulders like this one. So in this case, there's a potential of wave instability on the rock slope. Now, where do you can actually install this rockfall protection solution? You can install it on two locations. We divide it to two zones: source zone and runout zone. So those red line, you can see that is the rockfall possible rockfall trajectory once the rock detached from the slope. Okay, so it bouncing and go to the runout zone. On the source zone, with basically the rock surface, you can actually install the drapery system. In Malaysia, sometimes we refer this as a netting system. And for the runout zone, you have option to install this rockfall barrier. And in fact, this rockfall barrier, you can also install it on the upper part of the slope. So this way, if you're talking about the higher slope, you can install a series of rockfall barriers from the top of the slope to the toe as a rockfall protection. So this is just to illustrate the range of solution for protection. You have mesh system, and then we call it simple drapery and pin drapery. We'll cover that soon. And then barrier system. In this case, is a flexible barrier where it is different from rigid barrier. The whole thing will deform, especially the net. Talking about 5,000 kilojoule, the netting itself will deform maybe 7 to 8 meter long. So you need to provide a sufficient buffer zone when, if let's say you decided to use this barrier system. And debris flow is start to get more recognition in Malaysia after a few big debris flow event. So you can actually use a similar rockfall barrier system for debris flow mitigations. The only difference here is for rockfall barrier, you would normally design it as a point loading. So basically, you're talking about a big boulders that hitting the middle of the netting. Whereas for debris flow barrier, you have to design it based on the more uniformly distributed load from the debris events. Now, the last one is actually rockfall embankment, and this one you can actually see even a simple structure like a gabion can serve as a rockfall embankment. If you travel on along the LPT highway, you can see that certain gabion being built at setback maybe more than 10 meters. The whole idea is actually to contain any rockfall falling rocks from hitting the nearby vehicles. So this one is also another form of simple form of rockfall protection system. Now, when you talk about netting, the selection is actually a function of the weight. So the bigger the steel, the higher the tensile resistance as well as the punching resistance. Now, which one is important when you talk about simple and pin drapery? For pin drapery, the punching resistance will be more critical because there will be a tendency for the blocks to punch through the netting in between the anchors. Whereas for the simple drapery, because it is like a curtain, it doesn't really hold the blocks. It let it fall at the toe. All right. So for this case, it's more on the tensile strength resistance of the netting. So this is how it looks like, the punching test that you can carry out on the lab. So you need a bigger sample to consider the contribution of these. For instance, this one is a high strength steel mesh where we weave high strength ropes at certain spacing to increase the punching resistance. Just drawing the perspective here, for Gabion is about 30 kilonewton per meter punching resistance. By having the interwoven ropes, you can increase the punching resistance of about 15 ton, 150 kilonewtons. This is just to illustrate the range of the punching capacity of different system. Now, again, like I mentioned, for rockfall protection solution also, because you're using a steel material, mostly steel material, you need to be familiar with the type of coating you want to specify for the project. So you can even see here, there's a different classes for the zinc and even the galvan layer. If you don't specify this class, so for instance, you're looking at galvan 5% to be able to meet 50-year design life, you don't specify the class A or class B, you may end up with class B of only 25 years design life. So this is very important in terms of the performance specification like I mentioned just now. So you don't specify the brand, you actually specify what you need and what you assume during the design stage to be able to ensure that what is being supplied is what you assume during the design stage. All right. Several type of products or solutions for rockfall protection netting. This one is a high strength wire rope panel. Of course, it has a way higher punching resistance. Just now I mentioned high steel mesh is only about 150 kilonewton. This one can provide up to 400 kilonewton. The setback is this only come in 3 by 6 meter length roll, and you're talking about a relatively more time consuming installation as opposed to this high strength steel meshes, because these high strength steel meshes come in row. It's about 3 by 25 meter length, so you just have to drag the slope and you can do it fairly quickly. All right, this is okay. Simple and pin drapery, I've talked about this just now. So pin drapery, you can see here, is actually strengthening option that is combined with the rope for protection option. Hence, we call it pin drapery. And the second one is simple drapery. Simple drapery is really, it doesn't really hold the block. So you don't really need to be concerned on the punching strength. Rather than that, you focus on the tensile strength, because it's all about the amount of debris that you want to contain at the toe of the slope. And if you have space, you can put ditch, and if not, you have to pin it down, right? From based on this figure, this is actually the bottom pin down option for the simple drapery system. Now, this is how you actually can how you actually analyze this simple drapery. You can see here those red color is the debris volume that you design it for. It can be 1 meter cube, it can be 2 meter cube. The higher it is, the stiffer the system is going to be. So there's actually, this one is just using a simple limit equilibrium analysis assumption, and you can actually size the mesh according to the tensile strength requirements. And this one is one of the outputs from the specific software that been developed for this simple drapery. This is just to illustrate the more often than not, sometimes the accumulation of the rock is a function of the weathering. So the one on the left, if the rock is more prone to weather, you will end up with a bigger rockfall, a bigger volume of debris that being collected at the toe, as opposed to a more higher resistance on the right. Okay. So it's a function of the weathering proneness to the weathering of the rock slopes. This is how it looks like for the open option, where it's essentially just like a curtain. You let all the loose block to fall off, and the netting is just there to control the trajectory. You can see here the boulders is going to stop at the runout zone, where it will then eventually be collected and marked and clear from the site. This is how it looks like in real life. This one is at Bukit Cheras. You can see here is simple drapery system with high strength steel meshes, and you can see some spot of boltings here and there. That one is more on the localized stabilization of the slope. It doesn't really fall under the pin drapery category. And this is how it looks like at Jalan Duta at the top of the slope. So you need to anchor it on the top. Um, need to size the anchorage length of the anchor correctly, and pick the right diameter of the anchor rope on top. So this anchor rope will help to actually distribute the load to the anchor. This is actually a real life example in Malaysia, where the blocks is detached, and with this system, any type of high strength steel mesh system, it comes with a user friendly accessories, and you just have to open it up manually, clear up the detached block, and mark it up and remove it from the side. This one is at along Simpang Pulai Blue Valley. Again, simple drapery system. Also Gua Musang, simple drapery system with these high strength steel meshes. This is a pin drapery system. So I keep mentioning about for pin drapery, it's all about the punching capacity. So this is the free body diagram. You can see here there will be a tendency for the unstable block to punch through the netting between the anchors. So you need to be able to provide the right punching resistance on the netting, so that it will not be punched through by this detached block. Again, similar concept. How you actually determine the how big is the block going to detect is actually a function of the dip and strike of the rock slope. So this one, you need to do a proper rock slope mapping and identify what are the critical joints at before you're looking into the checking of the required punching resistance for the pin drapery system. Right, this one for pin drapery, for this case at Bandar Kirara, they use a high strength wire rope panels. And this one along the North Klang Valley Expressway, westbound, they use this also high strength wire rope panel for the pin drapery system. Again, this one is at Terowong Menora. If you travel to Terowong Menora, on the left side, you can actually see this pin drapery system that been installed there. This is at Gua Tempurung. So one of the things here you may realize here, you can actually also shotcrete the whole thing with this pin slope, right, with the anchored slope. But one of the setback of shotcrete, you need a whip hose for the groundwater that may pass through along the joints of the rocks. And if you use the netting, you don't really need that. And then point number two is really, if you have this netting, it looks better in terms of the environmental, in terms of the aesthetic looks, more natural looks, cleaner appearance, and also talking about the okay, now flexible rockfall barrier solution. Um, when we use term flexible, like I mentioned earlier, this solution is different from rigid, where you have to design the structure strong enough to take the energy or kinetic energy is been designed for. This flexible barrier, you want to design it flexible enough because the dissipations of energy is through the deformation of the various components. The we got this netting, and then we got these brakes, we got this post. So all of these will deform to dissipate the energy. Now, in the rockfall protection system, Okay, for the rockfall barrier, what you normally have to do, you need to do the rockfall trajectory analysis. From the rockfall trajectory analysis, what you get is you may end up with the velocity, design velocity as to from the trajectory analysis. So this design velocity you have to multiply by the mass boulders, the boulder mass that you identify, be it 1 ton or 2 ton, is a function of the unstable blocks that you identify during the rockfall mapping, and from there you get actually the energy level. Now, the second output from the rockfall trajectory is the bouncing height. Bouncing height is important to determine the exact post height for the rockfall barrier system that you want to pick. So two things that you have to consider for rockfall barrier: one, bouncing height. Second is the energy, which is a function of the boulder mass and the uh, velocity of the trajectory at the location where you want to place the barrier. Now, normally, how do you verify the performance of this flexible barrier? Just to illustrate here, this is the rock cache fence testing facility. You actually test the barrier almost vertical to the slope, 90-degree to the slope. And you can see here they use these concrete blocks to imitate the rock boulders at the side. So if you have 16.5 ton, 5,000 kilojoule, travel at 92 kilometer per hour, that is just to give you an idea about how 5,000 kilojoule looks like. And for this system, the netting will elongate maybe 7 to 8 meters. And this test is actually being covered by under European assessment documents. So one of the things that differentiate between the manufacturer is the testing verifications for the rockfall barrier solution. So you may want to specify the certification requirements in your spec just in case to protect you, because the elongation, for instance, you may have contacted several manufacturers and they have quoted a certain amount of elongations. So this elongation is actually being verified through this testing. So if you don't put in this certification in the spec, you may end up with a barrier that is not being tested under the European assessment document. This is just to illustrate the range of energy that it can be designed for. What interesting on this slide is actually on the upper part. You can see here RB335 and RB75. That is less than 100 kilojoules. And these solutions of rockfall barrier is suitable for the case of you only have smaller rock fragments, but instead of draping the whole slope with netting, it's going to be costly. Instead, you want to explore the usage of this low energy barrier for the rockfall protection. It will save much amount of money in terms of the cost of the project. Now, when you talk about the rockfall barriers, the most common uh, properties that you specify in the spec is only kilojoules. Like you need maybe 5,000 kilojoule, and maybe you put in some certification requirements like UOTA. Performance specifications goes beyond that. So for instance, I've mentioned just now elongation. All right, different manufacturer will have different elongations. It can be maybe 4-5 meter difference. It can be even more than that. We'll see how it looks like later. And then another aspect is the residual height, the lateral gaps, and lastly, the measurement of forces. Measurement of forces is more towards the optimization of the rockfall barrier design, where by having a lower forces, you require less anchor numbers for the installation. Hence, it will expedite the construction time. So this one is to illustrate the just now I mentioned point number one, residual height. You can even get the category C with EAD certification. The only difference is category A comes with 50% nominal height. What this residual height means is after the first impact, we will measure how much loss of height there is on the netting. All right. And this netting height cannot be recovered anymore throughout the service life. So if you specify a category A, you will have a higher buffer zone as opposed to category C, which is less than 30%. So they can manufacturer can still obtain the certification under category C, provided even though the residual height is only 10%, but if it can hold the boulder, they will get the certificate. What does it mean? You can see here that is the difference between even category A and category B. Okay, it may be able to retain the boulders, you will still get the certification, but with category A, you look at there, the structure is still standing still and it holds, it had retained a certain amount of residual height, still more than 50%. This is especially important if talking about the rockfall events where you have a subsequent detached block that may may travel to the netting before you start to repair the barrier. So it's important to look at the category A, B, or C when you specify the rockfall barrier. Now, the second point is actually the elongation. Like I mentioned just now, this barrier really elongates, right? The nettings, you can elongate maybe 8 meters, 5 meters, depending on the amount of energy it has been designed for. So what does this mean is when you check only with one manufacturer on the elongation and you don't specify these elongations in the performance specification, um, the contractor can actually supply any type of flexible barrier to meet only the energy requirements. So that is why for performance spec, maybe you should explore of adding this elongation value into the spec. And this one is lateral gaps. What does this mean is the gaps between the post and the netting. So once the barrier been impacted by the boulder, there will be a gap between the post and the netting. Just to give you an idea, the one on the left is without the lateral gap. So you can actually still see the gaps, but the EAD specify that the gaps we can consider it without any lateral gap if the opening is less than the mesh opening size. So in this case, it's less than 350 mm. So this is also important, lateral gaps performance, if you want to specify it. So imagine the boulder that may pass through the gaps in the middle. So instead of not specifying lateral gap, you should really be looking into it. Then lastly, this one is just a summary of the barrier comparison. Similar energy, okay, you can see here maximum elongation between manufacturers, difference 6 to 12 meter high, 12 meter long, and then residual height 70% to 30% category. So these are some of the additional performance specification that you maybe should explore, and you specify the rockfall protections for your roadworks. And this is just to illustrate the barrier performance after the impact. And you can see here is something that the flexible rockfall barrier has not been designed for. So if let's say the boulder hit the post, you have to replace the post together with the foundation. So this is something that is outside the limitation of any flexible rockfall barrier solution. Debris flow barrier, if you can see here, the component is the same. You got the netting, you got this longitudinal rope post. Again, like I said, the difference is only the design concept. This one you have to design it based on the uniform distributed load scenario. And this one is just to illustrate the rockfall embankment cases where you start to place this rockfall embankment for rockfall protection along the rock slope if you have space. This is not really often the case in Malaysia where we really have a space restriction along our highways. And early warning system, and this one is also some other innovation from various manufacturer. You can actually install also this early warning system to the rockfall protection, be it barrier or netting, and then we send a signal that the structure been impacted by the rock. It doesn't really measure any strain or any quantitative assessment of the slope. It's more on the warning system where it alerts the people's, especially your maintenance team, if you have a very limited resource, instead of inspecting the slope every month or every 2 weeks, you can actually install this and you can actually zoom into only the slope that with the problem. Now we have covered the rockfall protection. Now I just want to give you an introduction about the soil and facing. Um, These are the what being covered by BS 006. There are actually three type of facing that you can use for the soil nails. One is the hard facing on the left. The one on the middle is flexible facing, and the one on the right is soft facing. People often got confused with the soft facing and the flexible facing. And you can see there on the right, soft facing is actually only double twisted mesh with the geomat, whereas on the middle, flexible facing, it has some structural strength. So what does this mean is all the manufacturer use a similar netting for the rockfall protection, but they add in this geomat for vegetation growth. So basically, you install this and you start to spray the hydro seeds, and you will end up with a vegetated soil facing instead of short creek facing that is under the hard facing category. This is just a comparison between the type of facings. All right. You can see the soft facing is really meant for a very gentle slope with soil nail, maybe one vertical to 1.5 horizontal. If you're talking about 70 degrees, 60 degrees slope angle, flexible facing or hard facing may be proved to be more viable in terms of the technical requirements. And how you can actually size this one is actually we call it a hybrid method, where it's similar to the concept of pin drapery, but instead of checking the strike and dips, you actually want to verify the performance through this sliding mesh and base wedge concept. So you assume basically a wedge failure modes on the slope facing, and eventually you verify how much elongation does it take for the netting, and verify the required tensile strength required, as well as the punching strength. Um, just to illustrate, but in Malaysia, this is not really a common practice, but in other country, the soil spacing can go beyond maybe 2 meter or 2.5 meters. So the whole idea of having this flexible facing is it allows for the facing to take some of the loads, right? Instead of using only 1.2 or 1.5 meter spacing, you can actually explore of increasing the spacing. You utilize more on the netting, because netting is way cheaper, more sustainable as opposed to anchors. Anchor cost will be way costly to the netting cost. This is how it looks like. In fact, this one is been used in Malaysia. You can see here KL Metro project. They use a soil nail solution with this vegetated facing. This one is in Penang Hill under Penang Bandaraya. Okay, and then now we're going to talk about briefly introductions on the geosynthetic function for the road work improvement. So the work improvement here is actually a combination of maybe either drainage with a separation together with reinforcement or barrier. So let's look here. One is if let's say you want to have access road, normally you just lay a crusher run. The basic thing that you can do if the subgrade is even maybe less more than 8%, you can just CBR more than 8%, you can just lay the geosynthetic for the separation purpose. And for temporary, you just need it for separation. But whereas for permanent one, you need to consider the filtration. Then you're looking into the apparent opening size together with the permeability. All right. And then second point is that one is you can actually prevent the capillary rise from groundwater level, because this one is more applicable if you're using a finer base, where it will suck this groundwater and you have problems. And so to filter out this layer and provide an impervious barrier, you can actually install the liner below the road base, just between the subgrade and the base layer. Now, the point on the in the middle is actually the tension membrane concept. You can see here, once the wheel apply a certain loads to the base, right, we introduce the element of tension to the geosynthetics. So in this case, the vertical components of the geosynthetic will take the load. So this is the tension membrane concept. And imagine if you put this higher strength reinforcement, you can even sort of like act like a vertical restraint, especially in the weaker subgrade. This one more related to the baser reinforcement. It not just increase the one on the middle is about tension membrane concept and the vertical restraint. This one more towards the vessel reinforcement concept, where on the right is actually focusing more on the lateral confinement. This is where you install this extruded geogrid on the base layer. It provides a confinement effect between the geogrid and the gravel layer, for this case of the base course, and it increase the friction between these contact. We increase the lateral confinements and prevent the lateral spreading of the base layer. And lastly, the one on the right is actually the lateral drainage. Okay, it's more on the horizontal drainage application. Okay, this is how it looks like, extruded geogrid for the lateral confinement effect. So it's a bit like also like a geocell concept. In fact, geocell also can actually fall under the lateral confinements. So you may want to use geocell if you have the finer material. If let's say, for instance, you use sand as your base course layer instead of gravel, then maybe for that case, geocell may be more effective as opposed to this extruded geogrid, because it's all about the opening size of the geogrid. So the opening size has to match the gravel size or the size of the particles that you use for the design. And then this one is another concept where we talk about this asphalt reinforcement. So you can actually also reinforce the asphalt layer, and normally this one come together with a glass coated geogrid, and you can add in this separator together with it. What these do is, why they use this glass fiber coating is because to sustain the higher temperature during the paving process. Okay, the whole idea of this asphalt reinforcement is to reduce the maintenance cost and increase the service life. And in the certain aspect of the design, you can actually reduce the base cost layer by having this increased service life. So in the aspect of cost optimization, it reduces the thickness of these base course layer required. And this one is another introduction, vessel reinforcement. So when you talk about vessel reinforcement, these are the engineering principles that you need to understand. Tensile strength and elongation, anchor length and pull out. So this is more applicable for the tension membrane. Okay, make sure that you design it of a sufficient anchorage length. And in certain cases, even for the limestone area, all right, you may have to lay the reinforcement on both direction, okay, instead of only on one direction. Okay, so these are the consideration that you have to put in when you design for the vessel reinforcement. And then consolidation settlements. So don't forget the excess pore pressure be up. You even by having the reinforcement, you can't be putting in straight away 10 or 20-meter high of fill on top of it. You still need to allow for the strength gain on the foundations, and if required, you may want to expedite it with a PVD. So vessel reinforcement doesn't really reduce the consolidation settlement that much. So consolidation settlement will still happen. So you still need to rely on the strength of the foundations for the long-term case scenario. But the reinforcement was there for short-term stability. So you're talking about maybe without reinforcement, you can only maybe put surcharge of maybe 2 meter or 1 meter, and you have to wait for maybe 3 months. So instead, by having this reinforcement, maybe you can put in a higher surcharge, maybe 3-meter high, because this reinforcement will help to distribute the load better to the foundation. Vessel reinforcement concept, you can see the first one is you can actually use it for soft foundation, like I mentioned just now, for short-term stability, short-term safety factor. Normally you're looking at least more than 1.2, and you can even combine this vessel reinforcement with pile embankments. So it helps to distribute the load better between the subsoils and the pile head. Okay, by having this reinforced geosynthetic reinforcement, the pile head may be able to take more loads. And then lastly, better reinforcement also can be used for spanning the voids. This is a common practice, especially on the limestone area where you have a bigger cavity below the foundation. So instead of using maybe a pile, then that solution will maybe more problematic because you may end up punching through a cavity. You have to looking into the grouting of the cavity. So what you can do instead with this alternative option, a sustainable solution based reinforcement, you remove the piles. You use layers of base reinforcement. So base reinforcement doesn't have to be only in one layer. You can actually use maybe more layer depending on the design requirements. These are some of the products that you can actually use for base reinforcement. You have a geogrid, you have woven geotextile. Woven geotextile, you offer both reinforcement and separations. So this one is up to the design concept that you want to introduce for your project. And then, yeah, just to give you an idea about the horizontal application of the drainage, you can actually use this drainage geocomposite for to control the groundwater below your road base. So this is how it's going to be during the installations. And you can even place this geocomposite drain vertical application behind the retaining walls. This one may be applicable on the bridge abutments, right? Around the cover, you can also use it. Erosion controls. This one, geomat, the concept is actually to provide the shelter for the seeds to grow. You either have a biodegradable one, which means the temporary erosion control plus shelter, whereas the one on the right, geomat, with maybe double twisted mesh, is meant for permanent erosion control together with the shelter for the vegetation to grow. And over the time, once the vegetation has been established, it acts like a composite system together with the root system, improve the higher resistance to the erosion. And this one is just a picture where you can see on the left, no erosion control. The one in the middle is with the geomat. You can see a more greener look. There's the whole idea of sustainable solutions, and the one on the right is shotcrete facing. So you can actually decide which one looks better aesthetically. When you talk about geomat, it's all about the light penetrations. When we carry out the experiment with Colorado State University, we identified that there's actually the certain amount of light penetration requirements for you to get the vegetation to grow through the geomat. So it's about 40 to 70%. And this one is just about flood. So why we keep having a flood issue, and there's even a talk of increasing the flood ARI from 100 to 100 years is all about flood inflation. Because the during the study, maybe we only have a limited amount of data. So this one is all about the statistical distribution of estimating the peak flood. So it's a bit like we call it flood inflation scenario. And often people use a 1 in 100 ARI, average recurrence interval. That is maybe not, doesn't mean that the flood only will come once in every 100 years. What that is mean is actually maybe the right term you should be using the probability of the flood, 1% probability of flood that may happen in any years. All right. So that is actually some misconception or some confusion when you talk about the 100-year flood. In terms of the channel works, you can see here, channel comprised of suspended load and the higher bed load. Okay. Abrasion solution that I mentioned just now will meant for the suspended load. It's not for the coarse bed load. And when you design for the channel works, we often normally refer to referring to the velocity distribution. Why now we try the state of art now is moving away from the velocity distribution. We focus more on the shear stress approach is because the things that we are concerned with when you talk about river channel linings or river improvement works is the stress, the attractive force that been applied at the contact of the lining between the water. It can be in the bed or along the banks. Why velocity-based approach is not the right way to go now is you can only average the velocity. You can't be measuring the velocity at the bed or even on the banks. So what you can actually use here, you can start to introduce the shear stress based approach. It reflects it better because the higher shear stress will be on the bed load. It's a function of the water depth. The river banks will have a lower shear stress as opposed to the bed. Competence and capacity, this is another terms that you need to remember when you look at the channel improvement works or riverbank improvement works. So higher competence and higher capacity. Higher competence means that more size particle will be bring together. So similar case like a debris flow event that have been happening in Malaysia, it's all about the effective weight of the particles, buoyancy effect. So the dirtier the water is, the higher the density of the fluids. Hence, the lower the effective density of the particles, and that is where debris flow can even bring a bigger boulder with it because of these buoyancy effects, the reduction of the effective weight. Now, another thing is capacity. Imagine you have a similar channel with higher velocity, you will end up with a higher capacity, which means more water can pass through it. Now, in terms of the capacity and the competency, this is important, especially on the riverbank improvement works. You want the when you want to stabilize the natural channels, you want the roughness to be almost similar to the natural channel roughness. Ideal case, you can only achieve this with gabion because gabion allows vegetation to grow, and it will sort of like provide a roughness compatibility between the improvement work sections and the natural section. And secondly, this is also an important aspect when you're looking into the river crossing. If you have a box culvert that is very smooth, why you need to protect the downstream and upstream, because for higher smooth channels mean higher competence and higher capacity. So imagine these sediments that will be washed away at the toe due to the eddy bed currents, and hence why you need to be putting in the maybe mattress or even gabions, not just on the culvert outlets, across the bridge crossings and whatnot. And now, when you want to use gabions for any type of riverbank improvement works, you need to do two check because, like I mentioned just now, gabion has more roughness similar to the natural channel. So you need to check the flood level after a few years. Let's say the vegetation grow. So this one relate back to the mannings that you use. For the end of installation, the manning that you use may be 0.5. All right. After vegetation start to grow, you may end up with mannings of 0.7. What does this mean is higher mannings, you will end up with a lesser flood, a lesser Q, and it will increase the flood level. So you want to be sure that you won't get flood issue when you explore this gabion option along the riverbank. And this one on the right, you can see clearly the different in manning roughness of the channels after 11 years and just after the end of construction. So these are the things that you additional check that you have to do. Be sure that you check the flood level correctly before you implement it for your project. Now, in terms of the Gabion solution, you can actually use it based on location. You can use weir for the debris flow event, how you actually mitigate it. You can use weirs, combine it with sabo dams, and you can even, as you go travel through the sea, the gradient is slightly less. In this scenario, you can start to introduce the groin structures, and you can maybe improve the bank protection. And this is just to illustrate how it looks like along the riverbank, some of the intervention measures that you can actually use. So it's all about selecting the right roughness for the improvement works. So this one what you can actually use across the river on the drainage, and this one is for main drain control. So it's a bit different from what we used to do for the river bank improvement works along the banks. So normally when you have erosion, you just line it with gabions or mattress. Instead, for this groin option, you actually introduce a series of groins, and in a way you hope that the sediment will be built up between the groins and it meet the natural equilibrium naturally. Okay, this is in terms of the intervention, this is more time consuming. You're not talking about immediate repair or immediate effect. You can see after introducing it, and even you may have to introduce a series of groins over the years. Why Gabion is also suitable for the natural improvement work. Here you can see that filtration and permeability, because you're using rock facing option. It is a free draining materials, flexibility. It can tolerate certain amount of movement as opposed to the rigid structures. And the whole point of this sustainable solution with Gabion is you want the environment to integrate well with the structures. You can't even see the structures anymore. Again, just a recap from what I've mentioned just now. Gabion's durability is important. The right coating that you use, selection based on your design life, Class A, Class B, Galfan with advanced coating or with polymer coating, or you want to use zinc coating. So this one is all can be captured in this performance specification, where you start to talk about the right property for the function of your design. So Jennifer, I think that would be all from me, the conclusion, and maybe I open the Q&A session.
Yeah, thank you, IR Saifuddin. Now it's a very we are open for the Q&A. Thank you, IR Saifuddin, for the very interesting talk today for this morning. Participant, you can type in your question in the question box. Perhaps, IR Saifuddin, I have a question here. Well,
Yeah.
I'm looking at your coating that the medium, your coating for this dry condition, wet condition, and very high aggressive. So I wondering whether your any project that you are doing for the hill slope or high cut or high embankment expressway that for this Gabion wall, because let's say we have the constraint of the ROW, what is the condition that you are recommending or doing, and whether you do have any monitoring system throughout this say for 30 years, 20 years, all those, for us to confirm that the whatever we system that we adopted is working as site.
So it's a good question, really. But in terms of the measuring, you can only measure it once you start to see the corrosion. So nothing much you can do after you install Gabion on site. Okay. In terms of the, like I mentioned, for the expressway application, because it has to meet at least 100 years design life. So that's why we have been supplying these Galfan and polymer coatings for our Gabions. And the most interesting fact here, like I mentioned in my presentation, I've attended this discussion with one of the contractors together with the consultant. They are looking into a temporary works just with zinc coating. But unfortunately, that one is for river works. And I told them that with this zinc coating, you can't even meet the design life requirements of even a year with that. So they decided to use Galfan coating at least to meet 10 years design life for the temporary works requirement.
But let's say I have a project so-called the high embankment. I think you also know at this KL Kara area.
Okay.
Apparently when we go to the site, we can't access, but we look at the slope is quite high, and we are on the word that next we are going to do the widening. Whether how we do or adopt this kind of system.
You mean the selection of environmental level, whether you want to use C3 or C4, right?
Yeah,
Is that what
and
you mean?
also the type of your say your vertical slope protection together with the system and the coating that you are going to adopt.
Okay. So basically, this environmental level is not really something that one manufacturer come up with. So it's actually been covered in British Standard EN 10223. But what I can say here is this site environmental level relates to the corrosion rates, different corrosion rate in each country. So actually, if you Google for corrosion rate in Malaysia, that will actually guide you whether you're looking into C3 or C4 or C5. So for that particular location. So this is some quantitative classification that you can actually refer to. Okay. In terms of implementation, so again, when you know the environmental level, and then you start to look into the design life you want it to be. So whether you want to have a 50-year design life or 120-year design life, that is when they will tells you what type of coating that you should actually use for your project.
Okay. How about the cost as compared to a conventional system that
Like concrete
the
wall.
cost efficient of the yeah.
Yeah. So I can say I can make two comparison. One is this sustainable solution using flexible facing for soil nails. It is in Sabah and Sarawak especially, the cost of shotcrete is way higher. They prefer to use this netting for the soil nail system. Why? Because one, in terms of the cost, um, I'm talking about maybe 30-40% cheaper when you talk about the price of shotcrete in Sabah and Sarawak. Whereas in Semenanjung, it's a bit tricky because the cost wise maybe different only about 15 to 20% cheaper as opposed to shotcrete. And then a contractor may prefer to use the shotcrete option because of a higher margin they get with the shotcrete. But the things that they don't realize is with this option, they can actually expedite the construction aspect. Because you imagine if you want to shotcrete, you have to maybe use in different layers, right? Maybe two layers if it is 150 or 200 thick. Whereas for this solution, you can quickly install because if you use a high strength steel mesh, it come in 25 by 3 meter length. So imagine the amount of time, the amount of labor saving costs for the project itself. So those are the just to give you an idea about the cost comparison in terms of the production as well as the cost. Yeah.
How about this maintenance? The frequency of maintenance compared to short script.
Maintenance wise, like I said, if you design
Do you
it
have
based on
any so-called
checklist,
monitoring that checklist?
checklist we got I mean some even the rockfall protection, maybe you inspect it every year, you see the components whether there's some corrosion in it, and what you can actually do is you just replace that particular area. So you can actually patch a certain area if let's say you start to have corrosion. But so far, what I can say, if you specify Galfan and Polymac, you are on the right track to have 100 years design life without any problem. Because the problem that you may face with this type of problems on the dry condition is mostly if you have some scratch, right? Maybe the rock scratching the coating, then it start to expose the base wire of all the metallic
Yep.
coating. Then
Yep.
then
When
then
the
you start to have problem, right? So it's more on the physical and in water then it's different. It's more on the abrasion forces that been from these suspended sediments.
okay. Yep. I think we have the question from the audience. The question is, what are the maintenance work that we have to carry out after
Mhm.
completion of the project to enhance the lifespan of the structure by IR Chai?
Mm. So again, this is I can say that this is a free maintenance system really. The only maintenance that often been raised, let's say for the Gabions, for local authority, they talk about cutting the grass, right? That over the Gabion, so they want to clear the overgrown vegetation. So those are the kind of maintenance you're looking at. Other than that, because if you talk about concrete, maybe it's a cracking on the concrete, want to check, and then the whip holes. But whereas this one is a free draining system, if you place it on the rock slope, you can actually see water passing through it, right? So maintenance wise, for me is yeah, it's a free maintenance solution. It's all about just inspection to see any problem with for instance, the instability of the rock slopes and some overgrown vegetation, so those kind of things. So some cosmetic issue. Yeah.
Okay. Then the next question is what is the suitable gabion size used in Malaysia soil condition? Yeah,
So
this is
in
very good
Malaysia,
question.
yeah. So in Malaysia, actually, gabions, when you talk about size, the double twisted mesh opening in JKR standard, we always refer to by 8 by 10. So we're talking about the opening width of 80 mm. So when you look at, when you write the spec, you maybe specify type 8 by 10. In other country, they also have this gabion they call 6 by 8. So it's a slightly smaller mesh opening. So it offer a higher tensile strength. Okay. So in terms of gabion in Malaysia, the opening size, you need to use type 8 by 10. So that is common. And if you talk about size of the gabions, maybe 2 by 1 or 3 by 1, that depends on the construction preference by the contractor. What I can say, normally they prefer to install 2 by 1 instead of 1 by 1. Because if you want to have 1 by 1, you have to lace it at every meter. Okay, if you have 2 meter by 1 meter, then you only need to lace it every 1 meter, every 2 meter. So it expedite the installation process. Other than that, the in terms of size, I can't see much different really. It's all about the coating. What I can see, what we can actually improve in Malaysia is the coating aspect of the these gabions.
Let me check. In your slide earlier, you did present that the drainage system behind the retaining structure.
Yep.
Yeah. So whether that kind of drainage system, to reduce the pore pressure that to build behind the retaining system. Do you do any SI that or any monitoring system or SI before to check the groundwater table before you proceed to your retaining system?
Yeah. So basically, this one is a good question, really. That's why, as an engineer, we really need to understand the groundwater behind the wall or the slope that you want to build or the field you want to build it against to, right? That's why during the SI investigation, you normally, ideally, you want to at least put in some stem pipes, and then you monitor the fluctuation of the water for several months. Okay. Often than not, in Malaysia, the current practice we just rely on the water level that measured during the drilling process. This may not be the right water level depth, because imagine during the drilling process, if let's say you have the clayey materials with a permeability of 10 to minus 7, so imagine amount of water, amount of time it takes before the water start to dissipate, right? So that is why it's always important to monitor the groundwater level over a certain amount of time. So that is in terms of the investigation aspect. Nowadays also we have this what we call a vibrating wire piezometer, where you can actually put a sensor into the drill holes, right? And then this sensor you connect it to a logger, and it will measure the pore pressure within the boreholes over a period of time. And this one you can actually leave it there even during the construction if you select the right location where you put it into. You do not want to put this location of vibrating via piezometer or this standpipe on the construction area. Okay. So if you put it maybe further up, you can actually, while they're doing the construction, you can actually monitor still the groundwater or the pore pressure within the slope itself. In terms of the design, like you said, So normally we use Darcy law. So this one is quite common. Flownet is more if you involve with dams. When you have dams, like imagine you have the earthfield dams. So they have a impervious clay core in the middle. They will put normally a drainage blanket. So from here, how they size the drainage blanket is a function of the hydraulic head, right? H, the head of water behind it, and the length of the drainage blanket. So that you can see from this slide is I, hydraulic gradients. So from these hydraulic gradients and the area, which is the area of the blanket itself, the cross section. So whether you want to use a continuous blanket or whether you want to use maybe blanket of a certain spacing every 2 meter, from this area times by the hydraulic gradients and the permeability of the materials, you can estimate the Q that you allow for in the system, and then you cross check back with the Q that being provided by this geocomposite. So for sand, you know the amount of Q for the sand, right? So it's again same for the amount of Q for the geocomposite system.
Okay, noted. Understand. The next question, perhaps this one will be last question. What does the checking engineer need to do when the structure reach end of the assumed product working life? Do we demolish it? Do we enhance it? If yes, how? And take flexible slope facing, for example.
Yeah, so this one is a tricky question actually. So yeah, so I think you can actually see from the picture I've shown you earlier with the Gabions, right? In 1894, it is more than 100 years now, and yeah, I mean like they don't really have problem after 100 years. So again, if you talk about flexible fixing, if you after 100 years you start to have issues, many issues, then yeah, you need to start removing those netting and reapply it back. That's the only thing that I can think of. But in terms of the removal, it is I think it's way easier as opposed to shotcrete, right? Okay. So because you can just remove it easily, or even you don't have to remove it, you just apply additional or maybe a patches of netting at certain area where you have a concern, right? So you don't really have to maybe apply the whole thing. So again, this is subjective. I mean, like even the Gabions, 100 years, you can see that the wire itself is still intact.
Yeah. In short, that we need to do some maintenance work where required, where we don't see if the structure is still there, then it's still standing and working, then we don't need to demolish it.
Yeah.
Yeah. Okay. I think we reached about our time limit, 12 a.m. sharp, 12 p.m. sharp. So thank you, IS Saifuddin, for your very interesting talk this morning.
Thank you. I would like to apologize to the participant due to some of the disruptions, my internet connection here and there. So yeah. Anyway, you can feel free to contact me, and you can contact IEM if you want my emails, and then yeah, we can discuss further about any issues or any problem you have at the project.
Okay. Okay. Thank you.
Thank you.
And have a nice day.
You
Thank you.
too.
Thank you.